Unit 3 is all about the flexibility method of analysis of beams and frames. Of beams and frames. Okay, so we will directly take a problem. Okay, so all of you please take down simultaneously with me. So let us solve our first problem. So let me write it as problem 1. Okay, so the problem is based on a continuous beam. Okay, so the similar kind of problem we have already done in slope deflection method, moment distribution method. Okay, so we'll do analyze a continuous beam. So please take down the question. Analyze the continuous beam. Analyze the continuous beam as shown in the figure below. Okay, so how is the figure for continuous beam? Please check here. So the continuous beam is like this. So we have a fixed support. So this is our continuous beam. This is the fixed support. Here we have one ruler, and here I will be having another ruler. Okay, so this is A, this is B, this is C, and we have a UDL over here. So we have a UDL, and the intensity of UDL is, this is wait, just okay, this is 10 kilonewton per meter, 10 kilonewton per meter, and we have a concentrated load having magnitude 60 kilonewton. Okay, and the distance between these two, it is 3 meters, and this is also 3 meters. This one is 6 meters. And you have to take EI as constant. Okay, and you have to draw the shear force SFD shear, along with this, draw the SFD and BMD as well. Okay, so this is the question. EI equals to constant. It is saying EI equals to constant. Okay, so in the figure below, using flexibility method, using flexibility method. This we will try to solve using flexibility method. Now, before we go to the solution part, please tell me whether this continuous beam is a statically determinate one or an indeterminate one.
It's indeterminate one, sir.
Indeterminate. Why indeterminate?
There are more reactions than equilibrium conditions.
There are C. Okay, so if we take this one, if we take this problem, so here we have definitely, since it is a fixed end, we have 3 reactions. Okay, so one will be, wait, let me change this one. So one will be this horizontal, one vertical, one moment will be there, reaction here. This is one reaction here, another reaction will be there. Okay, so the number of unknown reactions is 5, whereas the number of equations are, how many number of equations we have? Equilibrium equations. How many number of equilibrium equations we have?
3, sir.
3. Okay, so 3 and how much are this one? So it is 3, 4, 5. Okay, so 5 minus 3 it is 2, right? Number of equations it is 2, right? Am I correct? Sorry, number, yeah, the degree of static indeterminacy it is. So let me write here. Okay, I will write it in red. Okay, so degree of static indeterminacy, ds equals to, this is 3, here it is 1, here it is 1. So 3 plus 1 plus 1 minus 3 again, the number of, so it is r minus r basically. Do you remember this? ds equals to capital R minus small r. So capital R is this 3 reactions over here, 1 reaction, 1 reaction. So 3 plus 1 plus 1 minus r is the number of equilibrium equations. So the 3 equilibrium equations, summation fx equals to 0, summation fy y equals to 0, and summation moment equals to 0, right? So these are the 3 equilibrium equations we have. Okay, so now, so here before, so you just remember that here the degree of static indeterminacy is equals to 0, 2. Okay, so now we have to do something in this problem in order to make this, or okay, so whatever we have done this one, this is your step 1. Okay, so before I go to the step 1, I would like to tell some equations. Okay, so we have a flexibility equation. Okay, so you can write this one, or flexibility relation. Now what is that flexibility relation? I'll just tell you. So flexibility relation is capital D minus small d L equals to F into P. Now you may ask, sir, why you are putting everything in bracket? Are we going to do something with matrices? Yes, we are going to solve this problem using matrices, and this flexibility method is also called as the matrix method. Okay, so here generally all the variables or all the things or components are expressed in terms of matrices. Okay, so this entire thing this entire thing is called displacement matrix. This one is called the flexibility matrix. And this one is called, what is this called? This we call it load vector. Okay, so in flexibility method, generally what we have to do, we have to, okay, now this load vector, or this you may call it as the load vector, the or this is also called as the force matrix. So instead of putting this slash, I will put or, because you may confuse. This is also called as force matrix. Okay, so everything is in matrix form. Okay, now you may ask, sir, what is the size of these matrices? So the size of these matrices, this will be in terms of, let me change the in color. Yes, the size of this one will be in n cross 1. This is n cross 1. This is n cross n, and this will be again n cross 1. So if you ask, what I will say, this is, instead of displacement matrix, I will also call it as displacement. Since it is a kind of column vector, I will call it as displacement vector. Okay, displacement vector. This I can also call it. So please don't confuse whenever I say the displacement vector, because the displacement vector or the displacement matrix are same. Okay, whenever it is like both are same, there is not an issue. But if it is a single one, then we call it as a displacement vector. This is flexibility matrix, and this is also called as force matrix, or you may call it as load vector, whatever you want to call. Okay, now what will be the size of this n? What is this n? Okay, this n is the, or it will depend on the degree of static indeterminacy. Okay, so if this value is 2, then this matrix, this flexibility matrix will be of size 2 cross 2. If this is of size, this value is 3, then the matrix will be of size 3 cross 3. Okay, similarly, the size of this one will be, what will be the size of this one? 2 cross 1. Do you understand what do you mean by 2 cross 2 to 3 cross 3? Do you remember mathematics, matrices?
Yes, sir.
Okay, so similarly, this will be the size of this DL will be again 2 cross 1. Okay, so without wasting any further time, let's go to the step 1. All of you can take this as step 1. So step 1 is degree of static indeterminacy. Okay. So what will be the degree of static indeterminacy? As I told here, the degree of static indeterminacy is, so ds equals to capital R minus small r equals to capital R is 3 plus 1 plus 1 minus 3. That becomes 3 minus, that becomes 0 2. Okay. So now this 0 2 means, so what does this 0 2 means? So this means that here any two reaction components, okay, any two reaction components are redundant or they are extra. Okay, so let me draw the same diagram or the same figure here for you. Okay, now this one. Okay, so this is A, this is B, this is C, and here we have a UDL. I'm not showing all the values. This is 40, yes, sorry, this is 60 kilonewton and this is 10. This is 10 kilonewton. Okay, so what I can say is, since the degree of static indeterminacy is 2, let us take the, or let us assume the moment over here. The moment over here, so let me put that one in other color. So let us take the moment that is MA and the moment here MB as redundant. Okay, so if I say the moment MA, MB are redundant, what does that mean? Okay, so this is basically an indeterminate structure. Okay, and here, so now see, in beams we generally neglect the axial deformation, right? Do we neglect the axial deformation? Axial deformation means there is no deformation in A and B, or no deformation in B and C axially. Okay, so what we will do is, we will, so if we remove, okay, let me show it here. Okay, so if we have a beam and we have a fixed end, okay, and we are saying that there is no axial deformation, so it means that here there will not be any kind of reaction. Okay, so basically here we will have this vertical reaction and this, so instead of this one we can make it as a hinged one. Okay, if we make it a hinged one, and if we show this vertical reaction over here, and definitely there will be one moment. Okay, so this we can write, or we can show it as, we have a beam over here, not a continuous beam. We will make it two separate elements. Okay, and this is hinged one. This is as usual, this B is a roller one. This is also a roller one, and this one is, by default it is roller. Okay, so this is our A, this is B, and this is again B, this is C. So this one is actually the determinate structure. STRUCTURE. Okay, please keep your doubts. Okay, whenever we finish this problem, because this problem is seriously going to take 2 hours, yeah, 2 classes, because you don't have any background knowledge of this method. So please keep your doubts. We will solve. I'll take those doubts at the end of this problem. Okay, that will be tomorrow. Okay, so now here what I need to say is, I am saying that the moments over here, I am taking the moments, this MA, and the moment over here, that is MB. I'm not saying that this will be in this direction particularly, but I am assuming that the moments here will be in this direction. So I am saying that, or I am taking these moments as redundant. Okay, so that I will write it here as, that I am writing it here as step 2, or let us continue with in the same step. So assume that, assume MA and MB as redundant. Okay, and this structure is called, or let us say this is the figure 1, this is figure 1, this is figure 2. Okay, so next we can say that the release structure is shown in figure 2. Okay, so here we have, so please don't forget that here we have a UDL. This is 10 kilonewton per meter, 10 kilonewton per meter, and we also have a 60 kilonewton. Okay, so now from this one, what we need to do? Okay, so we need to, with this figure, from this figure, we need to draw the moment diagram, bending moment diagram. Okay, so how we are going to do that? So you just need to extend these diagrams. Okay, this is the neutral axis again, this is again the neutral axis. So we all know, okay, this I'm writing it as bending moment diagram, just for understanding. So the maximum bending moment will be for this AB, for the span AB, where the maximum bending moment will occur. Please respond.
At center, sir.
At the center. Okay. At the center means it is where the load is placed. Okay. Yes, where the load is placed. Sorry. Okay, and what about span BC? It will be
Center.
not center, it will be an ellipse. Okay, so yes, the maximum bending moment will be at the center. Now, what will be the formula for this one? Do you remember the formula to determine the maximum bending moment?
WL square. WL by 4.
This is WL by 4. Okay, so WL by 4.
WL square by 8, sir.
And yes, this
Fan
one
beads.
WL square by
8.
8. Right. Okay, so this WL by 4 will be how much? So this is 60 into L is how much is L given in the question?
6.
6. So W into 6 by 4. So this is how much it is coming? This is coming as 90 kilonewton.
90.
Yes. So similarly, this one will be 10 into what is the length? Length is given as 6 meters again. So W into or 10 into 6 square divided by 8. So this becomes
45.
45 kilonewton meter. Okay. So next step is we need to draw the conjugate beam for this problem. Okay. So if we draw the conjugate beam for this problem, so again, sorry, this one is the beam, and since these are all simply supported ends, so the support will be the same supports. Okay, and here we will have the M by EI diagram again. Okay, and this one will be again so this center one will be 90 by EI, 90 by EI, and here at the center it will be 45 by EI. Okay, 45 by EI. Now this one will be, so since this is not the exact beam or this is a conjugate beam, we are saying that this is, let us say this is A dash, B dash, this is again B dash, and this is C dash. Okay, so the reactions over here, the reactions we call it as R A dash, this is RB dash, not only RB dash, this is, let's say, RBA dash, and this is RBC dash, and this is RC dash. Okay. So next is, I'll tell you what to do in the next step. So let me just keep it side here. So in step 2, what we will do, we'll calculate in step 2, we will calculate the displacement vector, or displacement matrix we also call it. Okay, I'm writing displacement vector. Okay, so the displacement vector is dl, right? I told it is d minus dl. I told you here, you see, I've already told that this is d minus dl. Okay, if it is d minus dl, then d minus dl, so this will be, one will be d1l and another will be d2. So since we have, if we would have got three the degree of static indeterminacy as 3, then we would have got another one, d3l. Okay, so this, now what is this d1l? So d1l is displacement at coordinate 1, displacement at coordinate 1 due to loading at, or due to given loading, okay. Next one is, this one is displacement at coordinate 2 due to given loading. Okay, due to given loading. Okay, so this will be, now what will be the displacement? So the displacements will be, so this is the coordinate 1 and this is the coordinate 2. Okay, so here we are considering the redundant moments to be acting. Okay, so here, so these displacements will be the slopes. Okay, so this we call it as theta A and theta B. Okay, if in the case of frames and all, the what will be the displacements? The displacements will be both theta and the displacements. Okay, so but here we have only the rotations. Okay, that is theta A and theta B. So what are the, so in order to have these theta A and theta B, what we need to find out? We need to find out, so this theta A, we need to find, or theta A we will get, if we, or this theta A will be the shear forces at A dash at the conjugate beam, okay, at here, okay, and this will be R dash A, and this theta B will be equals to the shear forces at B dash. So it is so if it is B dash, then it is RB, this one, RB A dash plus RB C dash. Okay. So now what is this RA dash, and can we find this RA dash from, can we find this RA dash and RBA dash and RBC dash? Yes, we can find from both these spans, right? So please pay attention here. So what I will write, so from span AB, from span AB, can we write RA dash plus RBA dash equals to 1/2 into, this is the length is, so half base into height, okay, the what will be the area, half base into height, right? So this length is again given as 6 meters, okay, so half into 6 into height is 90 by EI, so area divided by 2, so the whole area and divided by 2. Okay, so this implies RA dash plus RBA dash equals to 135 by EI. If you solve this one, then it will be 135 by EI. Okay, so similarly, from span B, this I can write it as not A dash B dash, this I can write it as from span A dash B dash, from span B dash C dash, from span B dash C dash R dash BC equals to R dash C, that will be equals to 2/3 the centroid, 2/3 into 6. This distance is again 6 meters, it is already given. Okay, six into 45 by EI, 4 divided by 2. Either you use directly, you can use this formula, or you can find out by considering these two members. Okay, these two has separate members and you can find out. Okay, no issue in that one. Okay, so this implies R B dash C equals to R C dash will be equals to, please calculate how much is this one. Please calculate, all of you.
Sir, R dash BC plus R is equal to, sir.
This is plus.
R dash
This is
BC.
equals to, not plus.
Okay.
Equals to.
So if you add both of them, we will get this value, sir. 2 by 3 into 6 into 45.
Wait. Yeah. Sorry. Sorry. So please calculate how much will be that value. How much is this one?
$90 by A, sir.
90 by EA. Okay. So what will be the next step then? The next step will be so here, so this one I am changing the ink color. So this one is no. Both of them will be same value, no? See, both the reactions will be same value. It's always confusing.
Sir, your voice is not audible, sir.
These two values will be equal. So this will be 135 by EI, and this will be again 135 by EI plus 90 by EI.
Sir, how it should be equal, sir? RA and RB, how it should be equal, sir?
Why RB and RA, this will not be equal? I am talking
Yes,
about
sir.
ये वाला देखो. Okay, let us say this one. Let us consider as this one here. This is a beam. Okay, And suppose here we have a load, whatever, let's say this is 60, suppose. Okay, so RA, this is RB, this is 3 meters. And this one is also 3 meters. Okay, so please, so what will be RA and RB? How much will be RA and RB? Huh?
It might be half, sir.
30.
Half, 30.
30, right? So this will be 30, this will be 30. So similarly, if instead of this load, if I have a triangular load, if I have a uniformly distributed triangular load, the same applies here, right? Okay, so that is RA dash equals to area divided by 2. So this is half into, so this is the base, this is the height. Okay, so a half into base is 6 meters into height is 90 by EI. So area under the curve divided by 2. That's it. So similarly, this is like this 2 by 3. So instead of a parabolic one, we have 2 by 3. So area of parabola is 2 by 3 into base into height divided by 2. Okay, so this will be R dash A, which will be equals to RB dash A equals to half into 6 into 90 by EI divided by 2. Similarly, this one will be RB dash C and RC dash will be 2 by 3 into 6 into 45 by EI. Sorry, 45 by EI divided by 2. So that becomes 90 EI. So if we add this one, so the shear forces at A equals to, so that will be 135 by EI, that is due to RA dash. Okay, and this is theta B equals to shear forces at B, that will be RBA dash, this one again RBA dash plus, so this is again 135 by EI plus RBC dash is 90 by EI, this one. So it is 90 by EI. So this becomes 135 by EI, 135 by EI, and this is equals to 225 by EI. That's it. Okay, so in the next class, we will go to the next step, that is how we will determine the flexibility matrix over here. We have the flexibility matrix, this one. So we